on the projector. And let's start the current slide. All right. Now, let me, I know you've heard them. Let me say them again for the people who aren't here in this class. I guess there's three. One's pretty major, though, okay? And that's the thing about payment. And if you or someone you know has not completed payment for fall term, that's supposed to be completed by today, okay? Today is the last time you can do it before you're going to get removed from the class. Unless you get in touch with the business office. Get in touch with them by phone, by email, go in person, and explain to them what your plans are, how you're going to get your payment done. They may be able to put a flag on yours so you don't get removed from the roll. So please, folks, try to get that done today. I announced it last time. I announced it today. But some of you aren't here. One of you haven't been here either day, so you haven't heard it. The others, I think, are okay. But anyway, please get that done. Okay, that's one thing. Another thing, I don't know, we've talked about the math team, and I thought you said you probably weren't going to be able to participate. But if you want to just to sit in on the practice sessions, you're certainly welcome. It can only help your math, okay? You know, are you pre-engineering or pre-math or math or what? Pre-engineering. What engineering?
Civil, but I might swap to electrical.
Okay. Well, what I was going to say is whatever engineering you're going into, sometime either after your junior year or sometime in the fray there, you will be taking your what they call the fundamentals exam. And it may actually be multiple exams. I don't remember. I don't know how many parts it is. It used to be called the EIT, Engineering and Training Exam, and it seemed like there were 4 parts to that. It's been so long I don't remember. I didn't take it. I wasn't an engineering major, but I had friends that were, and I remember it was a pretty major theme. And at least one of those parts back then was almost strictly math. Okay, so if that's coming up in the future, anything such as this would only be helpful for that, okay? But you're certainly welcome to be here if you want to participate in the practice rounds. You don't have to, practice sessions. You don't have to do the competition if you don't want to, but if you want to stay for this, you're certainly welcome. And then the one other thing, and this will be most Monday, Wednesday afternoons right after this class, 3:15, and most of the time we'll end by 4:45. Probably before then, but by 4:45, because Jasmine has a class that starts at 4:45, so we'll get out before that class. All right. Now the one other announcement, and this is not a major one. Normally on Fridays, my office hours on the Birmingham campus are 7:45 until 11:45. However, on Friday we have a meeting at 12:30. So effectively, that just extends my office hours until about 12:15 or 12:30 before I go. I'm not going to leave campus and come back, so I will have office hours a little bit longer on Friday. All right, any questions on what we've done so far? I hit that button, but nothing happened. Okay, maybe it will this time. Is it? Yeah, I think it is. All right. We finished 2.1 and are in 2.2, starting that today. Separable equations. It seems like to me, and just my way of thinking, this is where we should have started the course. But I'm afraid if we had, it would have been too confusing or messy. So I'm trying to follow the book. But to me, this is where we ought to be beginning. Okay? We begin our study of solution methods for the simplest of all differential equations, first order equation, separable variables. Now, what do we mean by that? We'll show you. Because the method discussed in this section and many other methods for solving differential equations involve integration, you are urged to refresh your memory on important formulas, okay, and techniques, integration by parts, that kind of stuff, and have your calculus text or reference handy. So, what if we have a differential equation? Let me get my pen set up. Okay, dy dx is equal to some function x and y. Okay, now, as a little bit of review, what if that was a function of y alone? What do we call that equation? Last thing we did in 2.1, or one of the last things. Okay, flick back a couple of pages there, and you'll see these are called the generic form is on page 39, equation 2. That's called an autonomous first order differential equations. Autonomous. No x dependence, only y dependence. Okay? Now, but if you do have x and y dependence, and by the way, all those autonomous differential equations can be solved using this, I want to say all, maybe not all, but most of them using the method we're going to be talking about, separation of variables, separable equations. But here we have a f of x, y. Now that function could have a variety of forms on it, okay? Now, if f doesn't depend on y, then if this f of xy is really just a g of x with no y dependence on it, that's not called autonomous, but look at what you can do. dy dx is equal to g of x. Okay? Now, this is called a derivative, right? Okay? What is it when we mean by differential? A differential, I mean, this is what it looks like. Technically, a pure mathematician would cringe to hear you say it, but it looks like you're multiplying by dx. Okay? To write this in differential form would be to write it as dy is equal to g of x dx. And guess what you can do to solve that one? Integrate both sides. Okay? What's the integral of dy? Just be y. What's the integral of g of x dx? I don't know, whatever its antiderivative is, if it has one. Okay? So you could call that capital G of x, and then you'd have a plus c. Unless, of course, you had some values that you know when y went from blah, 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 that x is going from blah, blah, blah. Then it's an exact differential, you know, and you can actually, you don't need a plus c. But that's how you solve if your f of xy is not really a function of y, just a function of x, you just integrate both sides. Okay? Now, what if, I don't want to get ahead of the book, all right, they give an example here, okay? I'm going to clean the page so we can start fresh. Okay? Here's an example. I can't see it. There it is. dy dx is equal to 1 plus e to the 2x. Okay? How would you proceed? Second? You're solving the differential equation. Okay? This is the derivative in a sense, but you first write it in differential form, which would be hate to say this because they don't like you to say, multiply both sides by dx, okay? That's what it looks like you're doing. What you are doing is writing in differential form, okay? And there you've got it in that form, and now you integrate both sides. What's the integral of dy? Y. What's the integral of 1 dx? The integral of dx. No, it's not 1. Integral of dy was y. Integral of dx is x. Okay, now this one takes a little more effort. Plus, okay, e to the 2x, and then the chain rule you would be doing times 2, but since you're doing an antiderivative, it would be divided by 2. And then you do your plus c. Okay? Now, if you're not sure you got it right, take a derivative, right? Derivative of y is dy. Derivative of x is dx. Derivative of x is 1. That's why I said it wrong. Derivative of y is dy. Derivative of x would be 1 dx. That's just dx. Derivative of this would be e to the 2x times 2. And the 2's cancel out, you get e to the 2x. Yeah, that's right. And then derivative of c is 0. You always have to have the plus c. Yes, when you're integrating, you got to have a plus c. So there is your thing. They wrote it slightly differently, but basically the same. X plus 1/2 e to the 2x plus c. Okay? All right. Now, equation 1, which is the thing we had when you just had g of x there, as well as this method of solution, is just a special case of when f in the normal form is f of xy, when it's not just g of x, okay? But you can still separate if that f of xy is written as g of x times h of y. In other words, you can separate the variables by multiplication. Addition doesn't help. Subtraction doesn't help. Multiplication or division, if you can separate them by multiplication and or division, those are called separable variables. Okay? So here's the form we're going to be doing. Separable equations, a first order differential equation of this form, dy dx is equal to g of x, h of x. H of y, sorry. Okay? That is said to be separable, or to have separable variables. I always called it separation of variables. Okay? Any one of those will work. Okay? So let's see if we can identify some. Okay? How about this one? dy dx is equal to y squared x e to the 3x plus 4y. Okay? Is that separable? What you think? Yay or nay? How? Show me how to separate it. Here's the first thing. Let's delete the y squared, okay, for now, and the x, okay. Those are just multiply. That looks like something's added. But the addition is in an exponent. And remember, if you have something adding exponents, that's the same as multiplying their powers. That's the same as e to the 3x times e to the 4y. If you got the same base, different exponents, multiplied, keep the base, add the exponents, right? This takes it back. Now this is obviously separable, okay? Your g of x would be x e to the 3x, and your h of y would be y squared e to the 4y. Okay? And your dy dx would be that. Right? Now separate them. Let's, of course, multiply both sides by dx, but also divide both sides by your y term. Y squared e to the 4y. Y squared e to the 4y. Okay? And you'll move your dx over here. That goes away, so you have dy over y squared e to the 4y is equal to x e to the 3x dx, and good luck with that, but you've got to separate them. If it's integrable, you can do it. Okay? Now, this one, okay. You remember how to integrate with something like this? Integration by parts. U equal x, dv equal e to the 3x. Then when you derivative of this, you get dx. Integrate that, and you get 1/3 e to the 3x. Okay? So yeah, you can make it separate, and then there's a rule to go from there. This one, on the other hand, is really going to be a pain in the neck to try to do. I'm not sure we have techniques to do that. You might try integration by parts to some extent, but actually, yeah. Rewrite this as y to the minus 2 e to the minus 4y dy. Then I think integration by parts will work. Possibly. I don't know. It's not going to be a pretty sight. It's going to be a little bit messy. But they're not asking you to solve it. They just said that equation is differentiable. I mean, is separable. Okay. How about this one? Dy dx is equal to y plus sine x. Now that looks a lot easier, doesn't it, than that other one did. But guess what? That one's not separable because it's not a product, it's a sum. Sums you can't combine like this. That one's not separable. This one is. It may not help you solve it any, but it is separable. Okay? So. All right. Now, they introduce yet another function there, p of y. Why? Why even mess with it? Just leave it 1 over h of y. I don't know. I don't see it's helpful any. Okay. They go through a lot of what almost looks like gobbledygook to just say you integrate. I mean, you do antiderivatives. It's just that that one has a very difficult antiderivative to see. May not even be able to, but boy, they just keep adding stuff and finally conclude what we just concluded. Yeah, you can separate it. Okay. And they do make a little point, and it's not a big deal. When you do separate, and say if you did figure out a way to integrate this one, and you use integration by parts and integrated that, okay? So you got your things. Do you need a plus C here and a plus C there? No. You only need one. If you had a plus C in both places, just subtract one from the other and it gives you a new plus C. So you only need one. First order differential equations only need one constant. Don't throw in another one just for the sake of throwing it in. Okay. So let's do example 1. Okay. Now they write this in what I consider differential form. Solve this. 1 plus x dy, I can't write. Let's see if I can make that read a little better. Minus y dx is equal to 0. Okay? Now, I don't know about you, but just looking at that, can you tell if it's separable or not? The answer is yeah, because you have a 1 plus x, you just don't have a y plus x. So as long as that's a function of x, that was a function of y, and you have your dy's and dx there, yeah, you can manipulate that. In fact, what I would suggest is adding a y dx to both sides. Okay? Pretty simple thing. So that would be 1 plus x dy is equal to y dx. Okay? Now, I need to separate my variables. I don't want x's with y's or y's with x's. I want to separate them. So I'm going to divide both sides by 1 plus x, but also divide both sides by y. Sorry. Okay. The last class, I was just getting hoarse, now I'm starting to cough. Well, here the 1 plus x's disappear, and here the y's disappear, and guess what? You got dy over y is equal to dx over 1 plus x. Yes, you've separated the variables. All the values, terms, and everything with y's in them, y's alone are on this side, all the x's are on the other side. You have separated them. Okay? That's just step 1, though. Where do you go from here? You integrate both sides, right? And what's the antiderivative of 1 over y dy? Do you remember that one? Okay, let me see. Yeah. Do you look? Oh, you don't have a book with you, do you? Okay, sorry. All right. I'll just tell it to you there. This is log y. Because derivative of log is derivative of log a is 1 over a. Okay. So yeah, the antiderivative of 1 over y dy would be log y. Now, technically, you need to put that in absolute values. Now, if something about your problem guaranteed that the y's you're dealing with are always positive, you don't need the absolute values. But if you don't know that ahead of time, put it in absolute values. All right, how about the right-hand side? How would you integrate that? Say again? I can't hear you. No, you have to integrate. Did you say leave it? Yeah, no, integrate it. Well, what is the derivative of that denominator? Just dx, isn't it? So you have dx, a derivative over the thing it's the derivative of. So again, this is the log of 1 plus x. And again, unless the problem indicated to you the x's were always positive or 0 or positive or just something less than greater than -1, then guaranteed that you could leave off the absolute value signs. Otherwise, you do this. Okay? And then the one last thing, because these are indefinite derivatives, you always have to do a plus c. And with a first order differential equation, you only need one parameter, c. All right. Now, here, before I say anything, I'll just see. No, they did. All right. That's their first step of a solution. Now, they actually call this a C1. Any time they do that, you know they're going to do something else to the problem to make it a little different, okay? And here's what they're going to do. They're going to exponentiate both sides of the equation. I'm going to carry it up here. So e to the ln absolute value of y is equal to e to the ln absolute value of 1 plus x, and technically you should still have the plus c1 here, okay, because you're exponentiating both sides. Now, why would you do that? Okay, well, e and logs are inverse functions of each other, right? Okay, so this would just be absolute value of y. And that's equal to, not quite so easy, unless, of course, wait. Remember, if we did have a sum of exponents, you could split that into e to the log absolute value 1 plus x times e to the c1, right? If you have a sum, exponential of sums, it's the product of the exponentials. Remember, that's the rule of exponentials. X to the 2 plus 5 would be x to the 7th, but that's x to the 2 times x to the 7th. I mean, x to the 5th, right? Okay, if you had x to the 7th, you can write that as x squared times x to the 5th, right? Why? Because when you're multiplying two bases, two powers, same base, different exponents, keep the base, add the exponents. Well, this is doing in reverse. Here we have e to the log 1 plus x plus c1 That's the same as e to the log 1 plus x times e to the c1. Okay? Now, that was an illustration. Let's get it out of there so it doesn't confuse the issue. Okay? Guess what? You can make that e to the c1 some other constant, because c is just a constant, c1 is a constant, e to the c1 is a constant. So we could rewrite this as absolute value of y is equal to, and then e to the log of this, that would be absolute value of 1 plus x times some other constant c. So you could put the c in front. Okay, now, here is a little deal with that. If y is positive, okay, this is a little tricky. To change an absolute value, this would mean, what would that mean? If y is positive, then this could be c, okay, all right. Let's do a few cases here. Y positive, 1 plus x negative. Okay? All right. The absolute values, that could be true, but because absolute value takes away all that. So either if you did log y, of course, okay. Wait, I'm sorry, I'm looking at the wrong place. I'm looking up here. What's that? Well, let's just assume C is positive. Doesn't have to be, let's just assume it is. Then, if C is positive and Y is positive, let's see how they approach this. I think they leave off a lot of steps here. Here's what they say. I'll do it. I'll see if I can rationalize it by what they're saying. Okay. Okay. So y is either equal to plus. Yuck. Okay. Y is equal either plus or minus c times 1 plus x. Okay. And here's why. Let's say y was positive. Okay, if c is negative and that's positive, then you'll use minus c times 1 plus x. Okay? Y is positive. Let's say c is positive, but this thing's negative. Then you use minus again. Okay? And if y is negative and c is positive, and this is positive, so it's going to be either one or the other. Okay? It's either going to be plus or minus c. Now, choose your c so that this is true. Okay? In other words, incorporate the sign into the c. If If y is positive and this is negative, then your c is going to have to be negative to make that work. If y is positive and c and x is positive, then c needs to be positive. If y is negative and 1 plus x is negative, then c needs to be positive. And if y is negative and 1 plus x is positive, then c has to be negative. Okay? So, incorporate the sign, whatever it is, of the c in with it to make it right. So basically then, you wind up with this as your thing. Y is equal to c times 1 plus x. There's your differential, there's your solution to the differential equation. And that is a single, I think I was one-dimensional, that's not what it's called. It's a one constant. They have a name for it. One parameter system. I couldn't think of the name. One parameter system, series of solutions. And if you don't believe it, take derivatives, okay? Derivative of this would be dy, and derivative of this would be multiply this through, that would be c plus cx. That would be let me rephrase that. Derivative of this would be, I think it's still, okay. dy equal derivative of that would be 0, derivative of that would be c dx, okay? Well, it's hard to do that on one, I suppose, but that will be a solution, okay? And you can go from there. So it's that is your solution. Y is equal to c times 1 plus x. Now, let's go to example 2. Now we have an initial value problem. dy dx is equal to minus x over y. Now remember we said it has to be separable into products, but a quotient is just a product of 1 over something, so it's still a product. But this time we have y of 4 is equal to negative 3. There's your initial value, or a value, okay? Now, what do you have to do first? Where do you go with it? 4 is equal to negative 3. That's your initial value. Where do you go with your differential equation? Yeah, you need to separate them. Okay, first thing we're going to do to separate is write it in differential form. dy is equal to minus x over y dx. Okay, that's done. Okay? But you want to get your y's together and your x's together. So what would you have to do? You want to separate the variables. Okay, no, you got the x where you want it with dx. You want the y with the dy, so what are you going to have to do? Multiply by y. Multiply both sides by y. Then this y goes out, and now you've got y dy is equal to minus x dx. There you're separated. And now what do we do? Integrate. Very good. I'm going to pull the minus sign out front. And what's the antiderivative of y dy? Derivative of y is 1. No, that would be 1 over y dy. This is y dy. remember when you were taking a derivative, you do exponent by coefficient, whatever your base is, you drop the exponent by 1, right? So if that was x squared and you're taking a derivative, it would be 2x. And then if that was x cubed, it would be 3x squared. Right? So that's taking derivatives. Antiderivative, okay, you increase the exponent by 1. And rather than multiplying, you divide by the new exponent. So this would be increase the exponent by 1. That would be y squared, and then divide by that. Y squared over 2. Remember that? Just to check it, if you took a derivative of this, be 2 times 1/2 is 1, y to the first power. That's exactly what you get. Okay? How about on the right-hand side? Minus plus some constant c. Okay, now I'm going to do something a little bizarre here too. I'm going to say c over 2. Okay, that's still a constant, right? Right? Still a constant. Okay, now I'm going to take that and multiply everything by 2. And you'll see why I did that. That makes y squared equal minus x squared plus c. Okay? Now, we may have a problem, Houston. This thing's always positive, isn't it? This thing's always negative, isn't it? Yeah. So, basically, I don't know. I mean, that makes it seem rather well. What we do here is add x squared to both sides. And what that gives us is x squared plus y squared, that's this side, these go away, is equal to some constant c. Does that look anywhere familiar? I can't ever remember what this book has in it. Not much. Okay. That is your equation of a circle, centered at the origin, right? With radius square root of c. Okay. That is an equation of a circle. So basically, the bigger c is, the bigger your circle is. So, you know, the smaller it is, the smaller it is. That's your equation of a circle, a series of concentric circles of at the origin. Okay. So what do we do from here? And by the way, that is one ugly 2, isn't it? My pen sometimes drags, and that was awful. Okay, there we go. Let's plug in our initial condition. Okay, when x is 4, y is negative 3. So if you put 4 squared plus a negative 3 squared, that's equal to some constant c. Well, what's 4 squared? 16? Okay. Plus, and what's negative 3 squared? 9. Okay. That's equal to c, so c is equal to 25. Okay, I know which circle that is. That's the circle of radius 5. Okay. So, There's a circle of radius 5. That's a pretty ugly circle, but yeah, given the idea. So you see, once you have an initial condition, you can figure out what the C is. Okay, there it is. Really ugly circle. Really ugly tick marks. Everything's ugly. Okay. So your final solution, I should write it down, is x squared plus y squared is equal to 25. Or you could say 5 squared, which radius 5. That's it. That circle, every point on that circle satisfies that equation. Okay? And that boundary condition. Okay. Now, before, when that was just a C, you'd have a family of solutions. 0, 0, when C is equal to 0. 1, when that's 1. 2, when it's, you have a whole family of solutions here. That's getting worse and worse and worse looking, isn't it? Oh, I messed that one up. That one goes there. Yeah, that's ugly. Shouldn't even be doing these. Okay, let me start over. Not all the way over, but part way. Then there's this circle here. So the concentric circle, but this is the one that has that point on it. 4 on x, negative 3 on y. That would be right over here, that point, okay? I don't know why that went there. Okay, everything I just drew is wiped out, but you saw what it was, a family of curves. The one that had 4, negative 3 on it, that was the one that solved the solution, the differential equation, and the boundary condition. Okay, now, one thing about that solution set, though, that wasn't a function. Y couldn't be written as a function of x because you had plus values or minus values. Failed vertical line test when it was a full circle. So if you wanted a unique solution, then it was either going to be plus or minus. The one that had the boundary condition was the one on the lower half. That would be minus the square root of x squared plus y. Okay? Now, they have a little blurb here on losing a solution. Some care should be exercised in separating variables since the variable divisors could be 0 at some point. Okay? Specifically, if r is a 0 of the function h of y, then substituting y is equal to r into that function makes both sides 0. In other words, it's a constant solution of the differential equation. But after the variables are separated, the equation, you might say, then might be undefined at r, okay? And so you have to watch out for that. I don't know if there's anything that needs to be said there. Let me go back to the one we just did. Yuck. And it's something I said which I shouldn't have said. dy dx is equal to minus x over y. Remember, that's where we started. Time out, team. Y can't be 0. Okay? So remember I said in that family of solutions, x squared plus y squared is equal to c. Yeah, if c were 0, then x and y have to be 0. The origin is a point. No, it isn't. Okay? Because you can't ever divide by 0. So even though it looked like a solution down here, if it messed up that, 0, 0 is not a solution. So even though it was perfectly fine in the family of curves, it's not perfectly fine in your original. So that, I realized I said it, and then when I read that, I said, no, that couldn't be a solution. Here's another one. Solve this. dy dx is equal to y squared minus 4. Okay? What would you do to try to solve that differential equation? And we don't have a initial condition, so we're going to play it by ear. What's that? Okay, first write it in differential form, right? What would that be? In other words, it's like you multiply by dx. dy is equal to y squared minus 4 dx. That's written in differential form. Have you separated your variables? No, you got x's and y's together over there, just y's over here. You need to do what? Divide by y squared minus 4. These go out, and now you have dy over y squared minus 4 is equal to dx. I can do the right-hand side, I think. But the left-hand side might be a little more trouble. Not really a lot. You remember how to approach one like this? It's called partial fractions. Remember early on they said you might need to review your integration and stuff, and that's integration by partial fractions. So let's take time out and do that. The integral of dy over y squared minus 4. What you do is take that middle part, let's leave off the dy for now. Just have 1 over y squared minus 4. Well, I know I can write that as some a over, because this is factorable, right, as the y plus 2 times y minus 2. So I know I can write that as a over y plus 2 plus b over y minus 2. Okay? That's where you begin. You know you can do that because it is factorable. Okay? So I think I'd write it like 1 over y plus 2 times y minus 2 is equal to a over y plus 2 plus b over y minus 2. Okay, now you could do it by brute force, but there is an easier way. And it doesn't seem like it's fair, but it is doable. Okay? What you can do is multiply everything on both sides of the equation by your least common denominator, which is y plus 2 times y minus 2. So multiply this with y plus 2 times y minus 2. Multiply this by y plus 2 times y minus 2. Multiply this by y plus 2 times y minus 2. Okay? Over here, that goes out, you're left with just 1. Right? That's pretty simple. Over here, the y plus 2's go out, and you're left with a y minus 2a, right? a times y minus 2 would be ay minus 2 times a. Okay? And actually, let's save ourselves a little trouble there. Let's keep it simple. Okay? Let's call this a times y minus 2 plus b, and the y minus 2's go out, times y plus 2. Okay? Keep it really simple. Okay? Now, here's the tricky part. And this doesn't seem fair, but it works. Let's choose a y. Okay? You get to choose any y you want to. Let's let y equal 2. Okay? This side is still 1. This side is, that goes to 0, right? And this becomes, if y is equal to 2, that would be 4b, right? Which means that b is equal to 1 over 4, right? Divide both sides by 4, right? Well, that works so nicely. Let's do something else. Let's let y equal minus 2. Well, this side over here is still 1, right? And if y is equal to minus 2, you have minus 4a. And then y equal minus 2 here, that goes to 0. So this produces, when you divide both sides by minus 4, that a is equal to minus 1/4. Okay? Now, let's back up. We've got what we needed. I'm going to erase a bunch of stuff because I don't have room to write anymore. Okay? I rewrote that at the top. I don't need this anymore. And what I'm going to do, a was negative 1/4. Yuck! This thing is so aggravating. Okay. A is negative 1/4, b is positive 1/4. Okay. Negative 1/4, b is positive 1/4. Okay. So let me get rid of all the rest of it, because that's all I really needed. Well, yuck. This thing is so aggravating. There we go. Sometimes it picks up the eraser and sometimes it doesn't. Okay. All right, now let's look at our integral there. Instead of 1 over y squared minus 4, we're going to rewrite this as the integral of minus 1/4 dy over y plus 2 plus the integral of 1/4 the integral of dy over y minus 2. Okay? Instead of 1 over that, it's a dy over that. So multiply each of those by dy's and then integrate them separately, and this is what you get. You know what that would be? Minus 1/4 dy over y plus 2 is your log. Natural log of y plus 2 plus 1/4 the natural log of absolute value y minus 2. Okay? So you've done this side. Now let's do this side. Integral of dx is x plus c. Okay. Now, that certainly is a solution. Can we stop there? Wish we could. We really shouldn't, okay? What we're going to do is this. It's another trick. Here's the trick. This is logarithms. Let's factor out the 1/4, okay, for now. And what we're going to have is log of absolute value y minus 2 minus log absolute value y plus 2, okay, is equal to x plus c. All right. Now, the rules of logarithms.
What do you do with the minus?
With what? Okay, what I did, I flip sides. I put this one here and this one there. Yeah. I wrote this one down here and this one over here. So the minus is here. I just factored out the 1/4 and had this one had the plus minus this one with the minus. Okay. And left that alone. Now, rules of logarithm. If you have natural log of something and a subtraction, that is the same as the natural log of the division of this by that. I don't think this is anywhere in your text. You're going to have to find a calculus text or a pre-calculus algebra text and find these. So this will be 1/4 the log of absolute value y minus 2 over absolute value y plus 2. Okay. And that's equal to x plus c. Well, we can just put the whole thing over absolute values. Yuck, I just don't have much room. I'm going to start erasing some stuff. Oops, that's not what I wanted to do. Let me start erasing here. We've already used this. I don't think we need this anymore. Okay. All right. So we'll do 1/4 the natural log of y minus 2 over y plus 2. Okay, just make it one absolute value rather than 2 is equal to x plus c. Okay? Well, then another rule of logarithms is the logarithm of number times the logarithm is the logarithm of the thing raised to that power. So this is the same as the logarithm of absolute value y minus 2 over y plus 2 raised to the 1/4 power. And that's equal to x plus c. Okay? Okay. Now what we can do is do an e of both sides. E to this, e to that. Well, e of a log is absolute value y minus 2 over y plus 2 to the 1/4 power. And that's equal to e to the x times e to the c. Remember that same thing we did with exponents before. Well, let's make that a new constant. So what we have now is y minus 2 over y plus 2 to the 1/4 is equal to some new constant c, k, whatever you want to call it, e to the x. Okay. Now, oh, yuck. Mess something up. at this stage, multiply both sides by 4. And that makes some new constant. So we don't need to carry that 4 around, that 1/4. But make this 4x e to the 4x e to the 4x. Okay, sorry, I should have done that. We're just out of time. Okay, now, if you drop the absolute value bars, you can make this a plus or minus. Okay, but making it a plus or minus, they do the same little trick that they did before. It's incorporate that into the C. So I'm going up here and try to wrap this up because we're out of time. Okay. All right, so what we have is y minus 2 over y plus 2 is equal to, and we'll incorporate that, c e to the 4x. Okay? Now, multiply both sides by y plus 2. Okay? So wipe that out. Okay? Now we've got y, let me erase something else because I'm running out of room. Okay. I'm sorry, this is a little tedious. It's not hard, but it's just tedious. Okay? So now we have y minus 2 is equal to c e to the 4x times y plus 2. Okay? Which would be y minus 2 is equal to c e to the 4x. I'm going to put the y in front. Plus 2c e to the 4x. Yeah. Okay. And if you move things around, like subtract this from both sides, add that to both sides, you get y minus y, or cy e to the 4x is equal to 2 plus 2c e to the 4x. Okay? Factor out the y, and you get y times 1 minus c e to the 4x. Okay? I probably dropped a sign somewhere. Is equal to this. Factor out a 2. 1 plus e to the c e to the 4x. Okay? And then divide both sides by this. So y is equal to 2 times 1 plus c e to the 4x over 1 minus c e to the 4x. Okay, and that's what, I've lost where it is now. That's what they've got here. Okay, and that's exactly the answer they have for number 6. All right, we ran out of time. Sorry about that. We'll start next time in example 4, but let me erase this. Homework exercises. Make good progress in 2-2. Do any of the odds 1 through 21, okay? And try to do any of the odds 23 to 27. And we didn't do example 5 yet, so you can stop there. All right. And we'll pick up and go from there next time. Make sense? Okay. Good deal.
Yeah, what's this section called?
This is called separable variables, or separation of variables. It's the easiest first approach. Once you get into integration stuff, things can get messy, but to set up the problem is pretty easy. Okay. All right, good deal. I'm going to shut this down.